Kristen Atchison here, and we're going to do an example problem for an independent group's T statistics. So, researchers have a special program that has been developed to help individuals get jobs, but is it different than the traditional jobs program? We have 7 people participating in the special jobs program, and we have 7 people participating in the traditional jobs program. So right off the top of the bat, just by reading this, we know we've got 2 independent groups. 2 independent groups, independent means t-test, right? So that's what we're going to do. We're interested in the 2 populations are those that are in the special jobs program and those that are in the traditional jobs program. So we're going to take a sample from each one of those. Now, this is inferential statistics. So we don't know the population mean. We don't know the population variance. We don't know any of that. So we're going to have to estimate that given the sample data, okay? We're going to start out with our research hypothesis that the special jobs program will make a difference in the number of jobs. That's our written research hypothesis or our written alternative hypothesis. Our mathematical expression of that is mu1 is not equal to mu2. Again, both of those are important. They're telling us that those 2 means of the population are not going to be equal. It's telling us that both in words and in symbols. Our null hypothesis is that the special jobs program will not make a difference compared to the traditional jobs program. So here we have mu1 is equal to mu2. So we have 2 groups with 2 independent means, and we're interested in making judgments and inferences about these 2 populations using our sample data. So, Group 1, our special jobs program, we do our data, and this is what we measure on our dependent variable and how many job offers they get. Okay, and we get a mean of 6 for the special jobs program. The next 7 people in our traditional jobs program, this is how many job offers they get, and we have a mean of 3. So we can look at this with our eyes. 6 is more than 3. So maybe the special jobs program is making a difference. But the question is, are the means different enough? Okay, we know they're different. We've got eyes. We've got basic math skills. My 8-year-old could tell you that these are different. But are they different enough to say that this difference is not due to chance? That it really is the influence of the independent variable, which jobs program you're in, on the dependent variable, the number of job offers you're getting. So again, we have 2 groups with 2 independent means. We do not know anything about the population, so we're going to have to estimate that, okay? And we're going to estimate that using the sample means and the sample variance, okay? And how we're going to do that, estimating variance should remind you of our friends sums of squares, and that's what we're going to do right now. So we're going to estimate the sums of squared. We're going to get our sums of squared for each group so that we can estimate the variance. So for group 1, we have a mean of 6. Again, this is my favorite way to calculate sums of square. In this table format, there's a whole separate video just on how to do it, where x is the data value. X minus mean is that value minus its mean, and then you're literally squaring that value and adding them together. So it is literally the sum of the squares, okay? So we get a sums of square of 24 for the special jobs program. For the traditional jobs program, we get a sums of square of 26, okay? Again, the question here, though, is, are the means different enough? And again, we're using this estimate of variance to help us make that decision. So our comparison distribution, we have 7 people in each group, right? So we have an N of 14. We'll have a degrees of freedom of 12 because we have degrees of freedom 6 for group 1 and we have degrees of freedom 6 for group 2. We add that together, we get degrees of freedom 12. And we're going to look at the difference between these 2 means, and we're comparing against the idea that there's no difference, right? That's our null hypothesis. It's called null hypothesis testing. So we're comparing against the idea that there's no difference between group 1 and group 2, which would mean that that difference is 0. Okay, so we have our sums of squared for group 1 calculated. Now we're going to need to estimate that variance. You should be familiar with this formula from 3510, sums of squared over degrees of freedom. Again, this is like the formula for inferential statistics. We use it again and again and again and again. If you have to memorize one formula, this is the one to do. I always joke that when I teach this class face to face, if I were to get a forehead tattoo, it would be sums of squared over degrees of freedom because we use it that frequently, okay? It's that important of a formula for inferential statistics. So just remember I have a forehead tattoo. You don't know, maybe I do. That says sums of squared divided by degrees of freedom. So our degrees of freedom is 6. We have 7 people in this special jobs program. So we get 6 for our degrees of freedom for this group. We know our sums of square is 24. 24 divided by 6 gives us 4. So our estimated variance for the population in the special jobs program is 4. We're going to do the same thing for the traditional jobs program now, okay? So for the traditional jobs program, again, my forehead tattoo, sums of squared divided by degrees of freedom. We have 7 people in this group. We'll get a degrees of freedom 6 for this. We know our sums of squared for the traditional jobs program is 26. 26 divided by 6 gives us 4.33. That is our estimated variance for the traditional jobs program. Okay, so we have these two values. We've got our 24 and 6 and our 26 and 6. We already knew this. We're going to also pool this variance, okay? This is another way to do that. So we've estimated our variance and we can use that in one way. The other way we can do it is we can pool our variance together. When we have equal groups, we can do this. And so it's the easiest way. We only have to do one calculation. And so in that case, what we'll do is we'll add the 24 and the 26 together, which gives us 50. And we'll add the 6 and the 6 together, which gives us 12. Our pooled variance for the study is 4.17. We're going to use that pooled variance in our estimated standard error, which is going into our T formula. So you can also use those estimated variance for each group as well. If those groups are unequal, if the groups are equal, pooling the variance is your best bet. So we have our pooled variance is 4.17. We have 7 people in each group. We have 4.17 divided by 7. 4.17 divided by 7. We'll add those two together. So we get 0.6 for each of those. Added together, we get 1.2. We're going to need to take the square root of that. So square root of 1.2 is 1.1. So our estimated standard error for this study is 1.10. That's going to be our denominator in our T statistic, okay? So that's why we estimated this standard error is to go into that denominator of our T statistic. Remember, that's our noise. It's saying, what is the variability in here? What does the variance look like in this sample, in this population? And would we expect this difference that we're seeing between the two means according to chance, based on this variability that we have? So we're doing a two-tailed test here because it just said, is there a difference between the two groups? It didn't say, did the special jobs group do a better job? It just said, is there a difference? Since we don't have a directional hypothesis, this is a two-tailed test. Our alpha level is 0.05. Our degrees of freedom is 12. When we look that up on our table, we're going to see plus or minus 2.179. Where we have 2.5%, that 5% is split between the two sides of our T distribution. And so we're saying anything above 2.179 positive or anything below negative 2.179 is going to be in our cutoff area. It's going to be in our critical value areas, and we're going to be able to reject the null. So I really like this meme because I'm a big stats nerd. I don't always have a p-value less than 0.05, but when I do, I'm statistically significant. The most interesting man on earth, you guys. So what we're doing with our T statistic is we're comparing the difference that we have between our two groups. That's mean 1 versus mean 2 of our two groups, compared to what we would expect to see in the population if the null hypothesis is true. That's that second part of that numerator in that T statistic formula. If the null hypothesis is true, we said that's 0. So we're looking at the actual difference between our samples minus 0, minus the idea of no difference. And we're going to divide that by this estimated standard error that we calculated. So for our test statistic, with our formula, we had a mean group of 6 for the special jobs program, a mean of 3 for the traditional jobs program. We're comparing that against the idea of no change, which is where our 0 comes from, and we're going to divide that by the variance that we're estimating based on our sample. That estimated standard difference here is 1.10. So we're going to take 3 divided by that estimated standard error of 1.10, and we're going to get a value of 2.73. Okay, so now we've got our t-statistic. Great. But we've got to go back and look and see if we could get this by chance. Or is there less than a 5% chance that we could have gotten this difference according to chance? And that's what we're going to do with our decision when we look at our t-distribution. So remember, we have that split, that 5% split up into both of the tails because we didn't have a direction. And we're going to be able to reject the null and support our research hypothesis. Our 2.73 falls into that cutoff area, right? It falls into that area that we said, hey, if you're here, then there's less than a 5% chance that we're getting this difference because of random factors, okay? So if you have problems with cutoffs or critical values, drawing the picture is always okay. You can even just draw yourself a number line and say, okay, anything towards the tails, towards the outside is where we're cutting it off. Is this number in that area? Here it is. So again, we're able to reject the null, support the research hypothesis. That special jobs program is making a difference. How we would write that finding out: the jobs ratings were higher for those who participated in the special jobs program versus those in the traditional jobs program. Notice we talk about both levels of the independent variable. We're talking about our dependent variable, we've got our means, and then we have our APA style statistical statement. We have T12, which is telling us which T distribution we're looking at, right? T12, that's our degrees of freedom, is equal to 2.73. That's our t-statistic that we just calculated. And we're saying that we're able to reject the null. Our p-value was less than 0.05 in a two-tailed test. That's what that APA style finding tells us really, really succinctly, so we can get all that information. Everybody can read that information out of that if you're familiar. So that was our first practice. We're going to do another practice where we'll give you can pause the video, do some time, and I'll hand calculate it so you can see how it looks by hand. Thanks.